Okay. So at least this time I'm a little more hopeful that my voice will last. Friday I was a little nervous, but now I know that my voice just sounds weird, and we'll do this. So week 14. So last week we talked about polymer dynamics. And specifically, we looked at the so-called Rouse model for the Gaussian chain. And the trick to remember was that we started with an overdamped equation for the individual beads, position Ri, making up our Gaussian chain, and we have the spring constants, interaction between neighboring beads, and a white noise. Now the trick was, okay, and so white noise, since I guess this was the first time you saw this, this means that the average is 0 and the cross correlation scale with the temperature. T, J, beta, T prime. And so the trick now was to go to a frame of the normal modes, where my set of equations can be written as rescaling the positions in the viscosity and the spring constant, such that I have a linear equation and noise as well. XPI. And that was possible with the definitions of this being integral over, sort of like in a sense, a little bit of some kind of thing, and rescaling also the spring constant accordingly. This gamma p was this odd 2 minus delta n 0 gamma. And with going to normal modes, we then had access to the dynamics, and we saw that the center of mass motion is diffusive following t equals 0. A diffusion that diffusivity that increases with temperature. And so this is the diffusivity. And then the to learn about the internal dynamics, we looked at the end-to-end distance vector. And learned that these dynamics tell us about the response of the system. So first of all, this ended up being a sum over the different modes. And here it was noteworthy to realize that the dynamics are governed by the largest modes, which are the ones that are biggest because of the exponential decay, at like p equal 1. Such that we identify that this is the relaxation timescale. And yeah, and then the second step was to see that the dynamic response is then related function of the frequency, or with which I'm also with omega-1 being these the mode, so 1 over this factor there. And this is really useful because this is something that we can compare in experiments. And indeed, I have a colleague next door who's actually even so nice to do these kind of experiments for me. So what you do is then you take a polymer and you shear it, oscillate it with a plate at a certain frequency, and you measure its response. And this has a real and an imaginary part. And so there's this plateau at which this would correspond to a regular spring behavior that we observe for the real part. And the imaginary part shows the viscous dissipation. And so indeed, these are properties that we can then measure and compare the response of polymers among each other, the match to experiments, and also the deviations and the differences between polymers. And then as a second, we looked at the weakly bending rods, knowing that we should take into account the semi-flexibility of polymers, and saw that for this, we can write down an equation for the undulations. This is going to looking at the weakly bending rod in 2D, 2 dimensions. So then we can write down an equation for the undulations, which is 4th order derivative and noise. So this corresponds to the 2D undulations. And from that, we can directly go to Fourier space and solve the dynamics in Fourier space. So, for example, these the frequency is then K, or kappa, sorry, this is a kappa. This is the bending modulus kappa. Kappa Q to the 4 gamma. And again, can calculate in a similar fashion the overall behavior of the chain and its response. And that was kind of like an outlook on going into the dynamics of systems, because these these are called Langevin equations for the motion. These are I skipped the gamma here. These are the key system that you can look at, describe dynamics with, and are going to be the topic of stochastic processes, which is taught by Uli Gerland next semester. And there's a whole mathematical framework that you can unfold to look into these systems. But we went further from looking at polymers to going towards polymer melts. Well, melts actually being the topic of today. Namely, we looked into phase separation of binary mixtures. And so the key here is that the free energy of a binary mixture consists of an this is a mean field description, and this would be the energy part. And then I have a T, write it this way, KB phi ln phi. This being the entropy, minus the entropy actually, mixing entropy. So there's 2 contributions describing our mean field well-mixed solution just by the volume fraction of, say, our solid in our solute in our solvent. And so there are two competing factors. One is the mixing entropy, which favors mixing, and one is the interaction energy, which, depending on the choice of the sign, favors mixing or a demixed phase. And this is all sort of looking at right now symmetric interactions. So that solute interaction is equally strong as solvent-solvent interaction. And just mapping out these two contributions, we see that the free energy as a function of phi, this being 1, this being phi equals 0, the entropic contribution is something like that. And then depending on how big the energy contribution is, this curve is out and has a transition to 3 maxima that are then shifting, over time. So this would be T bigger than a critical temperature. It would be at the critical temperature, and then these two would be below a critical temperature, where we observe a phase transition into, so the stable states would be the minima of the free energy, which are now demixed phases of, so this would be a half of the corresponding fractions. And we further saw that if we look at the second order derivative of the free energy, this was this magical spinodal. This aligns the stability of the phases, which means that, so down here, in this region, we have a single mixed phase. And then that is stable. In here, we are unstable towards demixing, and here it's metastable. That means that I need like some kind of starting point to drive the system towards demixing. And so just, to also, like, I had a good question after the class yesterday, on Friday. So how it works is that you take your molecules A and B, right? And you have them in certain volume fractions and you mix them together. And so if your volume fraction is, say, half, so you have half of A and half of B. If you're above the critical temperature, they will happily mix and just appear as like a happy, like a emulsion, like A's and next to B and B's are next to A. If I go below the critical temperature, then we would travel along this path. What would happen is that this half-half mixture becomes unstable, and droplets form that are either of a composition of, say, I don't know, just reading this off, 40% A and 60% B, and vice versa, 60% A and 40% B, right? So it's not that they fall into like only A's and only B's, but there's two distinct phases in the sense that they have different compositions in the ratios of A's and B's. And then depending on the temperature, the mixtures will become more and more. If I lower the temperature, the stable mixtures will become more and more pure. And so a half will always, below the critical temperature, will be unstable. So I prepare the mixture and just small thermal fluctuations, small wavelength fluctuations will drive the system to fall into these two separate phases. If I, however, choose a mixture that is, say, I don't know, 0.60% A and 40% B, so I'm in this metastable phase, I can be lucky that I prepare my mixture and it stays like that, because I have no starting point that drives them into falling into these phases. This is what it means. So you have to read this as like, you know, what is my starting condition and what are the phases that are stable in this context. On a conceptual level, what we learned looking at these phase diagrams was that there are multiple ways to determine the critical temperature, namely, first of all, the point where where I'll start finding 3 maxima. That's similar to the Ising model, right? So we see either when 3 maxima form. And we did this in this graphical solution, or looking at where this, you know, in the graphical solution, the line, like when is the slope equal to the slope of the tangent, tangent hyperbolicus. But what you can also see is that what happens here is that in the second order derivative, it's changing sign, right? So it's curved this way at a half, and it's going to be curved the other way around after we transition through the critical temperature. So a shorthand to find the critical temperature was also to determine when is the free energy respect to second order derivative at a half, the mixing favored entropy volume fraction, and when is this equal 0? When does this sign change? And that led us to a kind of known solution that's very similar to the Ising model. And one last thing, so what we also see is that we can determine these the composition of these stable fixed points as the F, the phi 1, the phi 2, like the two phases being equal to the chemical potential, which was termed the double tangent solution. Or construction, sorry. Construction. Yes. And then, so today, we're going to finish on the Flory-Huggins theory of polymer melts, and then think about droplet dynamics. Again, sort of taking this transition from this is the what we know about the equilibrium of a steady state, and we need, so this model is a little too simplistic. So we'll, standard thing is to use Flory-Huggins, but the essence of binary mixers is really captured by this diagram already, and then push into the field of non-equilibrium physics to think about the dynamics of how does this transition really take place. Namely, what happens in my impurity is that I have a small droplet forming, and then this droplet grows over time. And then this brings you very close already to current research topics. So returning to the Flory-Huggins theory of polymer melts. So what we saw, if we now consider polymers, so extended, like connected change of atoms instead of single atoms distributed on a lattice, is that the entropy has to be different, right? Because I have different space available to put down, you know, a polymer that has as a connected chain of atoms rather than if I just had to put down the atoms. And so the setting that we now consider to estimate this entropy correction is to say we have, say, m sites of our 2D grid. And now we have n polymers of n monomers each. And these are in principle, non-intersecting strings of n neighboring sites. And then that means that I have my amount of solvent molecules is then m sites. I have in total minus now n polymers and each n monomers long, right? So this is what remains for the solvent molecules. And now we want to calculate the entropy, we want to enumerate the microstates. And so the number of microstates is the number of states that I have available, faculty, divided by, that's easy, the states for the solvent molecules that are still atoms. And then I have to have some term that enumerates me the number of ways to organize these polymer chains on lattice. So this denotes number of ways to organize and note that also the individual polymers are indistinguishable, so they can commute. And so since these individual polymers can commute, we expect that there's, given that we have n polymers, and that this factor looks like small n faculty times the correction that then depends on how I can put down these n monomers on the lattice. That's already a little bit of an approximation. But it sort of takes care of this permutation. And now it seems very, very cumbersome to consider these, to enumerate these states. And if you did literature, obviously people did this, but actually it's fair enough to, as a good approximation to data, we can here assume that we approximate this concept, this term as a constant contribution to the entropy, which is obviously an approximation. And then we can redefine our volume fraction here now, phi, denoting the concentration of monomers. Right, so n times n, that's the lattice size that I have for my polymers, is then the volume fraction times m, the number of lattice sites. That then specifies that my small n can also be written as phi m over n. Exactly. And similarly, I can write now my number of solvent molecules as, which is m minus nn, as 1 minus phi m. And with this together, the entropy, that is skb ln omega, is, given the above approximations, KB ln of M faculty, and then the N1 was 1 minus phi M faculty. The small n was phi M N faculty, and then this constant. And then if we go through the game of, applying Stirling's formula again for M and N being large, we arrive at this really adding just up to a constant. And we find similar contribution here. And the only correction is that now here I have a phi over N popping up. Otherwise, it looks very similar to the correction for the binary mixture free entropy that we had before. And so then together the interaction energy can be written as also a function of JAB before. And so what we do here is, again, we assume that obviously a polymer monomer is very likely to be next to two other polymer monomers, right? Because it's a chain. And so I would expect statistically also to have more polymer monomer next to the polymer monomer than solvent monomer next to solvent monomers, right? Because there should be some bias. But this should be a higher order correction, and so we're disregarding this this bias. And this is so-called well mixed approximation. And then we can take those two terms together to find the free energy, which is a constant, and then M Z minus I T M. Exactly. And then this is typically written as a constant xi t kbt, and is the fit parameter to data, compromising all the interactions, and therefore called the interaction parameter. So really what's known as the Flory Huggins theory is then the free energy as a function of the volume fraction that has this psi of t and this is per monomer, right? Yeah. 1 minus phi, ln 1 minus phi. And this is typically fit to data. And often the scaling is A plus B over T, so two fit parameters that are being used. And this is what we need for looking at droplet dynamics. Quickly. Okay, so now having the Florey-Huggins theory, we turn to the question of droplet formation. So first of all, why do the droplets form? Well, that's what we learned from looking at the free energy of binary mixtures. This happens if the mix state is unstable. So because, and this is the case if the solvent and the interaction between, oh, sorry, just see a typo. This needs to be a BB. If the interaction between solvent and solute is, they are repelling each other compared to this interaction. So because the droplet material and solvent material repel each other. So that's the physics. And the physics is here the thermodynamics of phase separation. To really look into the dynamics of a solvent of the droplet, it's useful to also first of all recapture how I would describe an ideal gas. So as a short recap, the ideal gas, the free energy, this case would be KBT and ln n over V plus A, where this state, because the free energy doesn't account for energetic interaction, is counting the entropy, namely the number of accessible states. And to determine the state of a polymer of a gas, as we used already, need the chemical potential that is defined as dF dN, and in this case would be KBT ln n over V plus mu naught, where I summarize this mu naught as 1 plus A. And this says that we have n particles in a volume V at fixed temperature T. And then what is actually more useful now, instead of looking at volume fraction as we did for binary mixtures, is to think in concentrations. So we define, given that we have a fixed volume, we define the concentration as n number of particles per volume. And this allows us to write the free energy as KBT V times C, then ln C plus F naught. And similarly, then the chemical potential becomes KBT ln C plus mu naught. And this is what we're going to use shortly. So what does it tell us? What can we read off from this dependence already for the chemical potential? It fits here. So if I plot the chemical potential versus the concentration, has this logarithmic behavior. And this tells me that what I need to spend if I want to keep increasing, I mean, sorry, this looks like it's saturating and it's not. Let me try again. This is a logarithmic. Okay, there we go. Well, okay, yeah. So if I want to increase the concentration, I need to spend more and more, invest more and more in the chemical potential to allow for increasing the concentration. So the more particles there are, so the higher the concentration, the more difficult it is to insert an additional particle. And now we learned how to describe these to describe these interacting particles. Sorry. By looking at the polymer melts, which we're going to join here now. So we now describe the composition using a now note. Going to go to the volume fraction would be, note that this is a local property, right? Because the volume fraction will be different in the droplet and its surrounding. Fraction phi of droplet material. And now this we define as nu n over v in terms of like related now to the picture that we're thinking in concentrations. So here we have again the volume of the system. This is the number of particles. And V, the molecular volume per particle, right? Which we assume is a constant as N and V. Yeah, so but now, okay, so the molecular volume is constant, but now the number of particles in a given volume is something that can vary as we accumulate solutes into droplets. Since we assume and then obviously the solvent volume fraction, that's easy again, 1 minus phi, which is to say that we have a space filling liquid or void. And sorry, just to mention it, so this is now the relation of how we go from the volume fraction to concentrations. And so then we need what we just looked at, the thermodynamics of a homogeneous system. And for that we have free energy. which is proportional to the volume, and then the free energy of the volume fraction. And so this now has the entropic and enthalpic behavior. And in principle, this can be a different choice depending on what I want to look at, but the typical choice would be the Flory-Huggins. So can find it again. And now written in terms of these concentrations. And now, so again here the interaction parameter, the entropic, the entropic, and this is the energy. And this was this, sorry, not this one. This is the Flory-Huggins parameter describing effective interaction between droplet and solvent. And so from this free energy, we can now compute both chemical potential and pressure, and those two we need. So first of all, the chemical potential. That is the first order derivative, which we can also, now that this is written in terms of volume fraction, write as V F prime phi, and maybe let me, d phi dn. And since d phi dn gives a mu over v, the v cancels out, and so we can write this chemical potential as a shorthand as nu v prime of phi. And then we have pressure. Pressure is the second, the derivative with respect to volume, keeping temperature and number of particles constant. And so this is now again having expressed phi as a function of the volume fraction. We have minus before. Okay, so sorry. So we're taking this derivative, right, with respect to v. So the first derivative is just f, the free energy per monomer. And then the second term is v times f prime, and taking the derivative with respect to the volume fraction, which also has the volume in it. So that's phi. That's the first term, and then we have plus v f prime of phi, and d phi dv, which is nothing else but minus nu n v squared. Now we can cancel this and this, and identify what's remaining as this being phi again, to write this as a shorthand that P is minus sorry, there's a minus, not too many. Phi f prime of v minus f. And so these are the two thermodynamic variables that we now need if we want to consider now the setting of a droplet in the box and what will happen. So now with this in hand, we can go to thermodynamics of droplets. Okay, so let's consider a fixed volume. And I have a droplet. This droplet has a radius r and has a composition of volume fraction of phi in, and I have an outside volume fraction of phi out. So do here is consider two compartments. First, the droplet of volume. Sorry, volume. Right. And surface area. And the dilute phase of the remaining volume. Then we have a range of conservation laws. Namely, we have volume conservation, stating that however big the droplet and the outside, this has to give rise to the total volume, the system volume. And we also know that the amount of monomers has to stay the same. So we have another material conservation, which states that phi in, volume of I in times the volume fraction, plus the same for the rest, is bound to the total volume fraction of the droplet material. And now stating these conservation laws makes my life a lot easier, because I now know that these variables are not independent variables, but they depend on each other given a fixed constant. And with that, if we now return to our total free energy, considering now both solvent and solute, we have the free energy of the droplet phase and the free energy of the solvent phase. And in principle, we have another energetic contribution, which is due to the surface tension. So that would be a surface energy term. Okay, and now to learn about the system, we minimize, we're seeking the equilibrium state by minimizing the free energy and seeking the minimum. So we minimize F and look for where the partial derivatives must vanish. And so note, if we look at this, we have 4 variables, right? We have phi in, volume inside, phi inside, volume outside, phi outside. But I only noted 2 constraints, right? So we're still depending on 4 minus 2 makes 2. So I have to make a choice. And so since I care most about the droplet, I will use my two constraint to replace the outside volume and concentration and minimize with respect to the volume and the volume fraction of my droplet. So I have 4 variables and 2 constraints. So we eliminate and okay, so that means we have to do 2 derivatives. The first is that we want to have the f d phi in equals 0. And specifying that, we have the volume, then we have df, this term, and then the second term, we have v out, which doesn't depend on phi in, right? If we check up here, but now here we have to consider that the outer volume fraction depends on the inner volume fraction. Because if we solve our second constraint, we see that phi out is total volume fraction divided by, and so then this becomes minus v in v out, and nicely these two cancel, right? We also identify that this and this are the same. So the constraint that this total is 0 states that the derivative at phi in and derivative at phi out is the same. Like so. Which is recap the double tangent construction, right? That's the tangents are the same. Okay. Now we want to minimize respect to the volume of the droplet. So our next constraint is to say I want to have the f, dv, and maximized as well, minimized. And so here now it gets a little more tricky because note the volume fractions, sorry, this, for example, this volume fraction also depends on the inner volume fraction, right? So we get from the first term n, and then we get dv out dv in times f of phi out plus v out d f phi out. Sorry. Sorry, too many in. There we go. And note also the surface depends on the volume of the droplet. So we have another gamma dA dvn. Okay. So V out over V in, that's easy. That's a 1. And V out versus V in, this one, we had, that's minus phi in V out. So we find okay. Okay, something, let me just follow my notes. I must have done something weird here. Okay, let me see. So looking at phi out, d phi out, dv in. This is v out times. And d phi out. Sorry.
I think you just forgot the dependence of V out from V in, right? Because you just derived V in and then you get minus phi in over V out. But V out also depends on V in through the volume conservation. Like the thing you wrote before and then deleted.
This one. Sorry. The out also depends on the in via the total volume. Yeah. Is this what I'm okay. Let me quickly figure this. Yeah, exactly. So when taking, thank you. When taking the derivative here, there's a linear dependence directly of inner volume, but then also the outer volume depends via the total volume also on y in. So that's why I have to take the chain, make use of the chain rule. There we go. So we have copying down the, oops, sorry, denominator, and then we have a minus v out squared, dv out, dv in, and minus, and that's the this derivative v in phi in, sorry. Phi in v out. Okay, so now we go in and we cancel this one. Oh, sorry, wrong color. This and this and this, done. Okay, then we notice that where is it here? We have phi total minus v in phi in divided by v out is volume outside is just the volume fraction outside. So this here is the volume fraction outside and minus the volume fraction outside, and then v out, that's this here, as a function of volume inside is minus volume inside, so taking derivative, gives a -1. Yeah, much better. And then we arrive at the minuses cancel, v out minus v in. Okay, so that was this term. Where is it? This one? Oh, yeah, this one. And then we also have to deal with the surface term. So the dA dV in, that's the A dr, radius of the droplet dr dV in. Okay. The radius is the surface area is 4 pi r squared, so it's 8 pi r. 8 pi r, and then this I can write as 1 over dV in dr, which is then 1 over, and the volume, that's why I noted it, is cubic dependence, so it's 4 pi r squared. And so taken together, then we have 8 pi r over 4 pi r squared, it's 2r. And now our constraint becomes 0. F of phi in minus f of phi out plus f prime phi out times phi out minus phi in plus 2 gamma r. Okay. So now we derive two equations. What do they mean? So one means that the chemical equilibrium at the inner volume fraction is equal to the chemical concentration at the outer volume fraction. So that's chemical equilibrium. And the second, if we remind ourselves of the definition, here, look at that, the definition of the pressure. That was volume fraction derivative of the free energy minus F. So if we scroll down again, we have here volume fraction derivative minus F. Now, also noting that at chemical equilibrium, the derivative of phi out is equal to the derivative of phi in, right? This actually states here we are looking at a difference in pressure. So we're looking at P phi in is equal P of phi out plus the surface term. And that's sort of a mechanical equilibrium. Whereas this surface originating term is called Laplace pressure. Okay, so at least now we make sense of what comes out of just our mathematical procedure, and obviously the way to go ahead now is to solve for phi in and phi out depending on the free energy that we wrote down. But I don't want to go through the maths, but actually really just discuss the dynamics as a function of the free energy diagram. So mathematically, we would now here go ahead and solve for phi in and phi out. And that we know that we're interested in that there is a droplet phase separation is possible if there are solutions with phi in unequal phi out, if these are different. So the question we're really just interested in, when is this the case? And so to just gain inside, we'll look at the graphical interpretation of the Maxwell construction. Okay. And here now I will consider free energy where I have a curve like symmetric, something like that. Now we can look at the two conditions that we derived, right, in terms of the free energy. And so we look at this first without the surface tension term. It's Laplace pressure. So we said that the derivatives of phi in has to be equal to the derivative of phi out. And second, we had this and so if this is in this case, it looks like so this would be a construction where the tangent is the same on both points, and we are also obeying the second equation. Now, what would happen if I add here now the Laplace pressure term that comes into play? That would mean that I'm over that there's an offset in these curves that's proportional to the Laplace pressure. So what the Laplace pressure does is it increases the equilibrium concentrations. So we add up, we get a higher concentration of droplet material in our droplet. Oh, maybe stay with this. So Laplace and in detail, more detailed and reveals that the contribution of this Laplace pressure is proportional as an exponential distribution. So this is, in a sense, like putting what we learned about binary mixture in the context of droplets. And as I said, I again want to use this to move towards current research questions by now looking at the dynamics of droplet formation for the next 15 minutes. So what do we need to consider for the dynamics? Say we have compartments of concentration 1, concentration 2, concentration 3. which each correspond to a chemical potential mu1, mu2, mu3. Then I will have a flux that is proportional to the difference in chemical potential, right? So there's a so here, let's now consider an homogeneous system. So we start with an homogeneous system and we ask what are the dynamics of it. So then the change in concentration in this inner box is given by the amount of flux that comes in from the left and minus the flux that goes out to the right. So it's JL minus JR. And then the magnitude of this flux is given, it's proportional to the difference in chemical potential. And this is all happening over a scale delta x, that if we go to a continuous picture, what we have is that the concentration is a function of x, and also the flux is a function of space. And that then says that the time dynamics of my concentration are then minus the spatial derivative of my flux. And my flux is minus mu of my gamma dx mu. So taken together, inserted in the flux, I find that the dynamics are given by dx mu, which is a generalized diffusion equation. You might not have seen this before, but you have seen it actually for in the context of the ideal gas. So let's quickly consider the ideal gas to rationalize the equation that I just popped up. So remember, for the ideal gas, we had that the chemical potential was kBT ln concentration plus a mi naught, where the mi naught I don't know what this means, sorry. Oops. And then here, taking the spatial derivative of the chemical potential, I arrive at a kBT dx of C over C, right? So that means that then a term mu dx of mu, I can write as and what I'm going to do is I'm going to approximate the equilibrium chemical potential as mu naught C. And then adding the dx dc gives me kBT dx C over C. And then you already see that we're arriving at a mu kBT dx C, where this is a diffusivity. Again, where now dt dc is then dx of d dx C, namely if the diffusivity is constant, xc, normal diffusion equation. And so now, this is just to rationalize this generalized diffusion equation. And now it becomes interesting because now we, if we rationalize this generalized diffusion equation, we see that the dynamics of the concentration depends on the chemical potential, right? But then the chemical potential, again, depends on our free energy of our binary mixture, right? So knowing about the equilibrium description helps us also to think about the dynamics of the system. And so let's have a look at the Flory-Huggins free energy again. That was F is KBT over KBT B. Okay. Which is a complicated function of the volume fraction, but is actually for intermediate values of phi. We can approximate this as KB TV phi squared 1 minus phi squared for intermediate volume fraction. We do this because that makes it easier to now take calculate the chemical potential in this context. So the chemical potential is basically the derivative of this free energy per monomer. So that here then becomes phi 1 minus phi 1 minus 2 phi. And then from this chemical potential, the dynamics follow. Namely, that then dt of C is dx of mu dx mu, assuming this to be a constant. That is then mu dx squared of mu. So what this means is, if I sketch out my my free energy over phi, this one here. It means that I have a flux in that is proportional to the spatial gradient in the chemical potential, and so will drive the dynamics, the molecules close to the interface into the droplet phase, and so these droplets will grow over time, and how rapidly, depending on the actual outline of the free energy landscape. There's a correction that needs to be taken into account, which is again due to the dynamics of the interface. I have another correction that is proportional to the spatial concentration gradient at the interface. That's the energetic cost of the interface that gives rise to an additional contribution in this dynamics. But this equation alone is sufficient to explain so-called Ostwald ripening, which is the technical term for the coalescence of droplets. So if you, I don't know, think about the shower setting, right? You have small droplets, and these droplets will, coalesce over time as they meet neighbors, and you will have the big ones left that then are actually trailing down. That's the the Ostwald rightening effect. Those dynamics we can describe with the this extended diffusion equation, and this is then also the interface. In this case, we're still sort of looking at a dynamic process, but towards these dynamics will drive the system towards equilibrium, right? So what we take into account is the free energy landscape of the equilibrium system, and this is now telling us how will the system approach, what are the dynamics that are driving this, how the system approaches the equilibrium state. But as I had motivated looking into these liquid-liquid phase separation and droplet dynamics, what we have is that actually within our cells, there are energy-driven additional processes that are interfering with this concentration, because you're using your metabolic energy to bias the reactions that are driving the stability of these droplet dynamics. And this is the level at which you can then also add these fueled kinetics and then look at how the system actually finds out of equilibrium steady state, where the droplets actually don't grow to infinite size of like having the final binary mixture, but actually form droplets of a given specific size, which is actually the way of how life chose to use the physics to compartmentalize our individual cells, all the cells in the body. I always find this very mesmerizing to think about, like, we're using the physics really to understand how things are organized and all these crazy things that walking in a machinery to make a cell live. And not only there, like it's really a very rich phenomenon that's also used in the context of like building out of equilibrium systems by our friends across in chemistry, and really revolutionized how we think about again equilibrium physics of phase transitions in a very novel context. And with that, I'm actually concluding sort of the lecture part of this lecture. And on Friday will be, I will try to recap what you should have learned throughout the class. Thank you.